Hello everyone, we're going to look at average rate of change, which is going to be really motivational and the idea really for coming up with a derivative. We combine average rate of change with limits and voila, we get the derivative. So let's go ahead and look at what the average rate of change is. You can really look at this as kind of a more general form of slope. So the average rate of change of a function, and you need 2 points, let's say from x equals a to x equals b is, so I'll abbreviate it just by ARC, and it is f of x2 minus f of x1 divided by x2 minus x1. So you can see really the thing that's going on here is we're still looking at a change of y values over a change of x values. So in that respect, it's the same as the slope. The difference is you might have a picture that's a little bit different because your function is not going to necessarily be a linear function. It's not going to be a line. So when you're computing an average rate of change just with a typical kind of math example, the one extra step you have to do is you have to find those y values. You have to plug them into the function first. But let's go ahead and just look at the picture. I mean, I'll just do a general picture of maybe something that looks like a parabola. You might have, something like this. This is your function. And you've got your two values. Let's say a is right here and maybe b is here. So you find your points. So these points would correspond to y values over here, your f of x1 and your f of a and your f of b. Sorry, I said a and b and I wrote x1 and x2. So let me be consistent. Let me change these to a and b. You'll see it written both ways. I mean, there's no preference really for how you label your x values. So f of b minus f of a. All right. So then you have your two y values. So what we're really doing is we're calculating the slope of this dotted line. And that's that. So that's the picture. One other comment I want to make is when it does relate to units, you have a ratio of units here. So just as with the slope, the units of the average rate of change are units of y, or your units of output, per units of x. So units of output over units of input. Right, and that could be, a concrete example might be you look at a function where the input is time and the output is displacement or distance. In miles, let's say time or hours, then your average rate of change would be your average speed, miles per hour. Nothing too tricky there. So let's go ahead and just look at how we would compute this with a very straightforward and simple example. Again, there's not too much to this section, but it will be a primary motivating force for understanding the derivative. So example, let's say, find the average rate of change of f of x equals x squared minus 2 from x equals 2. I shouldn't use 2 so many times, it might confuse you. Let's say x equals 3 to x equals 5. Okay, so step 1, find your y values. So let's find f of 5. That's going to be 5 squared minus 2, which is 23. And then let's also find f of 3. That's going to be 3 squared minus 2, which is 7. So both of these kind of become ordered pairs. Then we just do the slope formula, right? We have 5 comma 23 and 3 comma 7. And then we just plug them into the slope formula, and that's how we get our average rate of change. So our average rate of change then becomes 23 minus 7 divided by 5 minus 3. So that's 16 over 2, which just happens to be 8. So that's exactly your average rate of change formula for that example. So let's do one more of these, then let's jump into an application example, and then that's pretty much it for this section. Not too much heavy lifting here in terms of new machinery. So let's find the average rate of change. Of g of x equals the square root of x plus 3. And sometimes you'll see it written like this. They might give you a specific interval rather than say x equals a to x equals b. So I'll write that in this fashion here. So let's say on the interval 6 to 13. So basically our first value is 6 and our end value is 13. So we're treating those as our x values that we're using here. But same as the previous example, we really just want to find the y values and then plug them into the ARC formula. So first thing we want to do is we want to find g of 13 and then find g of 6. So g of 13 is the square root of 13 plus 3, which is the square root of 16, which is 4. So our ordered pair here is 13 comma 4, and then g of 6 is the square root of 6 plus 3, which is the square root of 9, which happens to be 3. So our ordered pair in this example is 6 comma 3. So our average rate of change is going to be 4 minus 3 over 13 minus 6. So this just comes out to 1/7. And that's it for this one. Really exact same thing. We just end up with different average rate of change based on the function, based on the interval. Notice if we did the average rate of change for something where we had slope, like a linear function, the average rate of change would be the same no matter what interval, and that would just be whatever the slope of that linear function is. So let's move on to that application. Let's say that the balance of an account T years after it is opened is given by, let's say, the equation A of t equals 9,500 times the 1.064 raised to the t power. So as you recall, this is an exponential function with initial investment $9,500 and the base is 1.064, which indicates that there's 6.4% increase for each unit time step. So what we want to do is let's find the average rate of change, ARC, for 2.5 less than or equal to t less than or equal to 4.5, and interpret the result. So nothing really different about the way that we're going to find the average rate of change. Again, we're just plugging in both the t values into the function. So we want to figure out what a of 4.5 is. So that's going to be 9,500 times 1.064 to the 4.5. And then we go ahead and use our calculator to approximate that result. So that comes out to 12,559, and I'll round to the nearest cent, so 0.17. And then let's say we do A of 2.5. So that's 9,500 times 1.064 to the 2.5. So then let's type that into the calculator as well. So that comes out to 11,093.73. So then below, let's go ahead and compute the average rate of change. So the average rate of change is going to be the difference of these two outputs, 12,559.17 minus 11,093.73 over 4.5 minus 2.5. So just typing that into the calculator. So we get our answer of 732.72. And remember, what are the units of this going to be? Because we have to interpret. So the units are the units of output, which is dollars, and the input was years. So we know the output are dollars per year. So that helps us interpret. So that, since that's a positive number, it's corresponding to an increase. So it's telling us that during the time frame from 2.5 years after the account was opened to 4.5 years, the account earned on average $732.72 per year. So although the exponential amount is telling us the relative percentage increase per year, during the specific time frame, this is putting it in terms of actual dollars per year. Anyway, that's it. That's all I have to say for average rate of change. So we'll move on to limits next. And this is Dr. Lennon signing off.